In this video, we're going to have a look at some examples that use our basic indefinite integration rules. Remember to have the rules next to you so that you can keep referring to them as we work through the examples. So our instruction is determine the following indefinite integrals. So we need to calculate what they are. Let's look at our first example. So example 1, I need to find the integral of 2x to the power of 4 with respect to the variable x. Now, in this case, we've got the integral of a constant times a function. So let's go back and look at our rule. The integral of a constant times a function is you can take that constant out and just integrate the function. Now, remember when we integrate the function, we're going to use the power rule, which says that we add 1 on to the exponent and we divide by that. Then we add on our constant of integration. So let's do that. Right, so the integral, we're going to just pop that constant there, we take it out. Now we're going to add 1 to the exponent to get 5, and then we divide by that exponent, and we add our constant of integration. Now remember at the end to just tidy it up a little bit. 2x to the power of 5 over 5 we can write as 2x to the power of 5 over 5 plus our constant of integration. Alternatively, you can write 2 over 5 x to the power of 5 plus the constant of integration. Great, let's look at an example that's a little bit more technical. That's our second example. Okay, in this one we've got the integral of 4x minus 1 multiplied by x minus 3. Now you would have seen from our rules we didn't have an integral of a product. But that's okay, we can times these out and make it much easier to work with. So if we multiply it out, we're going to get the integral of 4x squared minus 13x plus 3. Don't forget, put it in brackets because you're integrating that whole thing with respect to x. So there's your dx. Now remember that we can split up our integral. So let's actually go back to our rules. You see here, if I've got an integral of a sum or a difference, I can split it up. So let's do that. Okay. Alright, so here I'm going to split it up. I'm going to find the integral of each one separately. Remember when we have a constant, we take it out. The integral then of x squared, we add 1 to the exponent, so we get x cubed, and we divide by 3. Now you can put that 3 just under the x cubed, or you can put it under the whole thing. I'm just going to put it under the x cubed in this case. We'll tidy it up just now. Minus, that 13 stays where it is. X, I've got to add 1 to get x squared, and then I divide by that, 2. Now remember, the integral of a constant will be the constant times x. So plus 3x, and don't forget your constant of integration. You're welcome to leave it like this. You can also just tidy it up a little bit. Actually, I can just tidy it up straight away. Let's do that. Just extend that line. Just tidies it up a little bit. You can always just go back and check yourself that you actually got the integral right. If I had to differentiate this, I would take out the 4 over 3. The derivative of x cubed is 3x squared. The 3 on the top cancels with the 3 at the bottom. There we go. I would take out the 13 over 2. The derivative of x squared is 2x. The 2 cancels with the 2 at the bottom. The derivative of 3x is 3, and the derivative of a constant is 0. Cool, let's have a look at another example. Alright, so in this example, I'm finding the integral of 3 over x to the power of 4 plus x to the power of 4 over 3. Now you can see that we don't have integral rules for quotients, but we can immediately rewrite these guys as powers, just like we do in differentiation. Don't forget to keep your integral sign until you've actually integrated. I can rewrite the first one as 3x to the negative 4. Then I can rewrite the second one, because remember when we wanted in power form, we wanted in coefficient base exponent. So this is the same as a third x to the power of 4. We take that third to get our coefficient. Remember your brackets, and you're integrating with respect to x. Now we can work with each one of these separately. Okay, so when we integrate something with the constant comes out. Then I've got x, and I add 1 to negative 4 to get negative 3. And let's actually extend that line straight away now. We divide by negative 3. Great. Next one, plus that third comes out. Then I add 1. And I divide by what I've added as well. Don't forget your constant of integration. Now what we can do is just tidy this all up a little bit. You can see immediately that 3 and that 3 cancel. So I've got an x to the negative 3 over negative 1. Now we don't like writing our final answers with negative exponents. We want to tidy it up a little bit. So let's write it with a positive exponent. This is negative, so we keep the negative 1 over x cubed. Here, tidy that up a little bit. We've got 3 times 5 in the denominator. So I've got x to the power of 5 over 15 plus our constant of integration. All that. And then you can go back and just check that actually if you differentiate those, will you get back to this? And you'll find that you do. So let's look at our next example. Example 4. Alright, so in this particular example, we've got the integral of root x minus 3x cubed. I've put this one in just to make sure that you know how to handle a root. But we do it in the same way that we do when we differentiate. We make sure we can write it as a power. So this is the same as finding the integral of x to the power of a half minus 3x cubed with respect to x. Alright, so let's invoke our power rule straight away. Let's add 1 onto a half, which means that we get a half plus 1, so it's a half plus 2 over 2, which means we get 3 over 2. And we need to then divide by that same thing. And you'll see in the next step we can actually have done that in a bit of a prettier way. But I just want to stick to our rule for the moment. Minus, now the 3 stays, we add 1 to get our 4, and we divide by 4. And don't forget to add on your constant of integration. Alright, so let's make this first guy look a little bit prettier. If we divide by 3 over 2, tip and times says it's the same as timesing by 2 over 3. So that's how we get 2 over 3 x to the power of 3 over 2 minus 3x to the power of 4 over 4 plus our constant of integration. We can tidy that up and make it look even prettier. Let's not have a fraction exponent. Let's rewrite that. So we know that we can rewrite that as, so I've got 2. Now x to the 3 over 2 is the same as the square root of x cubed. And then it's my 3. Remember, you could have left that 2 over 3 out in front as well. Minus 3x to the power of 4 over 4 plus your constant of integration. So that's how you deal with the root in your question. Okay, let's have a look at our next example. Now, in this particular example, we've got a function divided by a function. Like I said, there's no rule in our integration rules that allows us to deal with quotients. But again, just like we do with derivatives, we can split each term in the numerator over the denominator and deal straight with our power rule. So let's do that. This is the same as finding the integral of x cubed divided by x squared plus 5x squared divided by x squared minus 4 over x squared integrated with respect to x. Let's simplify those. So this is the integral of x plus 5 minus 4x to the negative 2, because we want those all in nice power form. Now we can use our rules. Remember, if you're integrating x, you want to add 1 to get x squared, and then you divide by 2. The integral of 5 is 5x, because the derivative of 5x is 5, minus, take out the 4, then you've got x, you want to add 1, so it's the negative 1, divided by negative 1, plus your constant of integration. Alright, so let's just tidy this up a little bit. We land up with x squared over 2 plus 5x. Now here we have a minus and a minus, so that's a plus 4. We don't want a negative exponent, so it's over x plus our constant of integration. Right, let's have a look at our last example. Right, so let's have a look at this one. In this example, again, I've got that root. So we know we don't have a integration rule that deals directly with the roots, but we know what to do with that. We can raise it to the power of a half instead of writing the root. So this is the same as integral of 1 plus x over 2 to the power of a half, integrated with respect to x. Right, so now we're going to be looking at that last rule. So actually, let's go back to our rules for a moment. We're looking at this rule here, just an adapted power rule to a linear function. Because believe it or not, 1 plus x over 2 is a linear function. So what we do is we have 1 over the coefficient of x times by linear function, and we add 1 and we divide by 1. Okay, so let me show you that that is in fact a linear function, just in case you didn't see it. So let's actually just rewrite that x over 2 as a half x. Then it's easier to see it as a linear function. Cool, so when we integrate that, we're going to go 1 over the coefficient of x. And we can, 1 over a half is 2, but I'll actually write it as 1 over a half to start with. Okay, just so that you can see I'm using the rule, times by, now I've got 1 plus a half x. Remember, I add 1 to half, and I get 3 over 2, and then we divide by 3 over 2, and we add our constant of integration. Now let's just make that prettier, and we could have gone straight to this step, definitely. In this one, 1 over a half is 2 times by that 3 over 2. I can immediately rewrite as 2 over 3. Then I've got 1 plus a half x to the power of 3 over 2 plus my constant of integration. Okay, make it even prettier, simplify further, that becomes 4 over 3. Now the 3 over 2 we know we can rewrite as a root, so I've got 1 plus, and you can leave that as half x, so you can write it as x over 2 again, to the power of 3, and you take the root of that. And don't forget your constant of integration. So let's just use this example to see why in this case, right up here, we had to go 1 over that coefficient. If I had to go back and I had to differentiate this function here, 3 over 2 would come to the front. Okay, it would then cancel with that 3 over 2, that's why you don't see it here. I would then subtract 3 over 2 minus 1, which gives me a half. Then according to chain rule, I'd have to go inside and differentiate 1 plus a half x. The derivative of 1 is 0, and the derivative of half x is a half. So I need that other half in order to cancel it out, because I don't see a half in that function. So that's why this rule works. Maybe have another look at this example. It's probably the most technical one, but you'll see that as you get into the flow of it, it's not too bad.